I'm going to be using Jump Pro, although all the features I'm going to show today are in standard Jump. I'm using version 17. Most of what I show today would be consistent with Jump 16 and Jump 15, but in the sample size explorers that I'll touch on a little bit, they have changed. They're nicer, more functional in version 17. So with your annually renewing licenses, assuming that it's okay with your company to upgrade to 17, we would encourage you to upgrade to 17 whenever you can. All right, today we're talking about reliability. And I'm just going to start with a light bulb example. And let's see if I can make this work now. There we go. So this is a pretty simple little example. It's kind of goofy, but it illustrates what we're trying to do with reliability, just to get everybody on the same page. This is called non-repairable reliability because when a light bulb burns out, it's done. We don't fix it, we throw it away. There are many examples of this. If you have a part that is going to eventually fail and you're not going to repair it, then we're talking about these non-repairable tools. And in this case, for this particular example, we're interested in how many times can we turn this light bulb on and off before it fails. The data are completely contrived. I made this up. So it's not going to be, if you're in the light bulb industry, it's not going to make any sense to you. It won't look right. But it's illustrative of what we're trying to get across. All right, so we would like to know things like what percentage of bulbs will fail after 1100 on-off cycles. That might be one question that we ask. Or maybe it's how many on-off cycles will cause 50% of our bulbs to fail? It kind of turns that question, that first question, inside out. Those are the kind of things that we might like to study about this failing light bulb. If we're going to figure this out, of course, we need data. If we're going to estimate a failure rate, we need data. So the test parameters might be something like this. We've got 100 test fixtures in our lab, so we can test as many as 100 bulbs. We have a way to measure each bulb. Somehow we're not sitting there watching every bulb switch on and off. Maybe we've got a current sensor or something that tells us whether the bulb has failed or not. So we have an accurate count of how many of these on-off switches happen before the light bulb fails. The other requirement is that we can only test for 800 hours. So remember, one of the questions might be how many of these things are going to fail by 1100 hours? Well, we only have 800 hours to perform this. I'm sorry, I said 800 hours. This should be cycles, on-off cycles. That's as many as we think we can do before we need to get the lab space back. So we're limited in the amount of time or the amount of cycles that we can put on these things. Well, that's problematic because we're trying to estimate all the way out to 1100 cycles. So what are we going to do? And forgive me, obviously we've got one typo here with hours. I may have done that in other places as well. So forgive me if we spot those. Okay. So we collect some data. We've got these 100 bulbs that we're switching on and off, and some bulbs fail pretty quickly, maybe after 400 on-off cycles. And some may fail later, maybe at 700 cycles. Many, in this case where I generated the data, 37 out of the 100 bulbs were still running after 800 on-off cycles. Sorry about that. So let's plot the results and see what we get, just with a simple bar chart. This is what that distribution looks like. We had some small group of bulbs, some small number that failed within the 400 window. We've actually got data on this, but just using the bar chart, we've got a few here at 400, more at 500, more at 600, more at 7, more at 800. But that's where our test stopped. We've got another 37 out here that made it past 800. I've got them listed here at 900 cycles. Where else are you going to put them? It's good data. They made it to at least 800. We don't want to throw that data away, but what are we going to do with that? So the blue bars represent the actual failures, and the red bar indicates censored data. Well, what if we believe that the actual failure distribution of these parts is a bell-shaped normal distribution? So if I can keep my mouse showing here, it would start here and the bell shape would come up, maybe peak here around 800, and then should tail back off if we were able to test on out to 1,000, 1,200, 1,500 cycles. We should see that normal distribution. Well, how are we going to get to that? We could fit a normal distribution just to this data over here. And if we did that, if you can see it, there's a broken line here. If we were ignoring all of these that survived all the way out past 800 cycles, we would get a normal distribution fit, but it would be biased low. It would be indicating that we've got more early failures than what we actually had, because we're ignoring all these that actually made it past 800 cycles. If we include all those and we call them, say, 900 cycles, well, that seems to make things fit the data a little bit better, but we're still kind of skewed. We're not fitting it very well. And the reason is, what are these that made it to 900? Should they be 1,000? Should they be 1,100, 1,200? This group that made it past 800, these are called censored observations. They didn't actually fail. This is very common in reliability. You're going to run product, you're going to run some set of samples, and some of them are going to fail and some of them are not. Those are going to be censored. How do we handle that? Well, JMP's reliability platform called Life Distribution is how we handle that. And what we'll get out of that, and I'll show you how to get here in just a minute, are charts like this, these profilers. The first one here says, what is the probability, the output, and in this case it's 17.4%, of our product making it to 611 on-off cycles. 611 on-off cycles is 17% within this 95% confidence range. So I believe that somewhere between 12 and 24% of my data, of my units, are going to fail by 611 cycles. And we can drag these around. This is PowerPoint I'm in here. I'll show you how to do this in a minute. But we can drag these around like other profilers in JMP to get estimates of what's our failure rate expected to be at 500 cycles, or at 700, or at 800, or on up past that. If we flip that chart around, we can say, when do we expect 50% of our product to fail? So our probability is 50%, and we can, whoops, I'm sorry. There we go. We can read up from 50% and across and get, we expect 773 on-off cycles should result in 50% failures. Actually, it'll be somewhere between 730 and 818 for our 95% confidence intervals. So that's where we're going. All right. So I generated up some data. This is what a typical data set for reliability might look like. So here we've got this first column is really not used, but it's just the unit that we're testing, the light bulb number that we're testing, from 1 down to 100. In this case, we've got 100 bulbs under test. And we start switching these bulbs on and off, and bulb number 1 lasted 568 on-off cycles, and then it failed. It would not turn on anymore. Well, that's real data, so that is not censored. That's what this third column is. That tells us if that particular unit was still running at the end of the test, or when we describe it here at 568 cycles. Unit 2 made it to 567, and it failed. Unit 3 made it to 726, and it failed. Unit 4 was still running at 800 cycles. that means it's censored. We don't know how much longer it would have run, but it ran at least to 800. Okay, so to analyze this, we're going to go to Analyze and Reliability and Survival, and then the very top one here is Life Distribution. Our time to event is cycles to failure. Now, I'll just mention here that I'm working with cycles, but it's what is stressing your product. It doesn't have to be cycles. It could be minutes or hours, or it could be bending stress. You know, how many cycles of that might it be? Whatever that stressor is that you're applying and relieving, or the length of time when something is under a load, that kind of thing is what we're going to put in here to our time to event. And then we have to tell JMP, this is the column. Remember, we had ones and zeros here in our sensor column, so this is going to be our sensor column. Over here, we get to tell JMP, what does it mean to be censored? That sensor column should say failed, or could say failed and running, or it could be 0 and 1, or it could be ones indicate failed and 0 indicates censored. This is where you would describe that. In this case, it's already, JMP's assumption is correct that a 1 means it's censored. So we'll just say okay. And here's our output. Now this first plot simply shows us our raw data. So here's our cycles to failure and our probability of failure. Each one of these dots along here is a unit that failed. So if I hover over one right here, this is row 58. The bulb in that particular row of my data table failed at about 650 cycles, and that was the 25%. That accounted for about 25% of all the dots in my data. About 25% of them fell below that. That's kind of how you read this chart. We also have these what are called non-parametric confidence intervals around that. So this is interesting. This is just the basic view of your data. Up here, we get to choose what kind of data, what kind of function fits this data. Now, I built this data set. I know what it is. It happens to be normal. I'll show you what to do if you don't know in just a second. But I'm going to fit a normal distribution to that. And now we get to see that we've got this kind of greenish line that fits the data, and it should fit pretty well since I forced it to be a normal distribution. And it's got the 95% confidence intervals around that normal best fit. Notice up here at the very top, there's a few points up here. These represent those units that made it to 800 cycles. So these are censored up here. These are all failures down here. JMP has taken these into account and has built them onto the tail end of the distribution. This is that first distribution profiler that we saw in an earlier slide. And if we wanted to say at 700 cycles, what percent of our product do we expect to have failed? Well, our best guess is 32%, 32.6% within those confidence intervals there. Just like with any data, with any analysis, any statistical analysis, more data is generally going to reduce your confidence intervals, give you a better estimate of the result. So here you can see that we don't perfectly fit that normal distribution line. And because of that, we get some error in our estimates. Okay, so there's our distribution profiler. If you're interested in what did JMP estimate for the mean and the standard deviation, you'll find those down here in the parameter estimates. Just so you know, I actually put in a mean of 800 and a standard deviation of 150 when I generated this data. So given the random noise in the data and that I had 100 samples, it came pretty close to getting the true grand population answer. And the the confidence intervals would certainly capture those. Well, right here. So I said 800, the mean is between the two of those, and 150, the standard deviation is between those. This distribution profiler down here is exactly the same as what we saw up above. The second one, the quantile profiler, flips the two axes. So now we can say, when do I expect 10% of my light bulbs to fail? Well, I expect 10% to fail by 564 cycles between 518 and 609. If I'm looking, the hazard profiler is if I'm looking at an instantaneous failure rate. What's happening over time with these things? Are they starting out at a slow failure pace and then increasing in that pace of failures over time, which is what we're seeing here, at least up to 800 cycles. It looks like as things get older, as they get more wear and tear on the light bulbs from these start-stops, that for any given time, I'm going to be seeing more and more failures as I get further and further out. And then the density profiler is the shape of that density curve, which in this case, we've assumed to be a normal distribution. So there's our normal distribution. Okay. Back up here to the top. I mentioned that this is a normal distribution because I know it is. But what if I didn't know what that was? You may have insight into your data that says, you know, for instance, a Weibull distribution is based on your particular failure modes. You expect it to be a Weibull distribution based on the physics of what's going on. Or maybe you expect it to be a log normal distribution. Or maybe it's a Frouchet. That one doesn't look like it quite fits as well. If you don't know what the statistics are or what the physics are behind your distribution, how do you know which one of these to pick? Well, you can ask JMP to pick it for you. From the red hotspot, all we have to do is say fit all distributions. JMP goes through and builds and fits distributions for all of these different types of curves. And it rank orders them in order of the what's called the AICC, the Akaike Information Criteria. Akaike Information Criteria is a goodness of fit metric, and low numbers are better. So the lowest number is the best one you can get, which in this case turned out to be a log normal. Now you'll see down here, this was the one, when I set this data up, it should have been a normal distribution. But look at how close these numbers are. Between a log normal all the way down here to a logistic are within about 2 points of each other, 2.5, 3 points of each other. Generally, I've heard different guidelines on this. If AICC, if the numbers are within 2 points of each other, they're statistically the same. They're modeling the same data. They've got the same goodness of fit. If you get up to 4, a lot of people think even 4 points is okay. If you go a lot beyond 4 points, like this exponential distribution, let's check it out real quick. Where's exponential? Here we go. There's the exponential distribution. Clearly, that does not fit the data very well. So, so it has thrown that one out. The rest of them are all almost the same. Maybe this defective subpopulation Frouchet and the SEV, maybe they're not good. So that's the idea. You can let JMP find that distribution for you, or you can specify it yourself. And once you specify one, let's say we specified log normal up here, you'll get the log normal report down here with all of your distribution profilers. Let me show you real quickly the sample size explorers and just tell you a little bit about what they do. And then we'll spend a couple of minutes on accelerated life testing. Okay, so sample size planning. There are a couple of tests in JMP. Let's see, I can put this away. And this is going to be under the DOE menu. So under DOE and down here at the bottom is sample size explorers. This is where jump 17 is going to look a little bit different than jump 15 and 16 and prior versions. And then here's reliability. We've got three options here. The first two are really meant for if you've got a product and somebody says, and you claim that it lasts 1,000 cycles, and somebody claims, prove it. That's what these first two are for. How many samples would I have to test, and how long would I have to run them in order to prove that I get to 1,000 cycles, for example. The last one is how to set up a reliability test. So let me just show you these real quickly. I'll just go to these over here. This is what the parametric sample size explorer looks like. So we're saying we want to demonstrate, in this case, 50, maybe this is 50,000 hours, something like that. How big does our sample size have to be? Showing 0 failures to demonstrate that 90, I can't show you that, that should expand. It should say 90% reliability. Well, I'd have to test 50 samples for 37.7 hours with 0, or 37.7 thousand hours in this case, with 0 failures to demonstrate 90% reliability, assuming a Weibull distribution, 95% confidence, and the shape parameter applies to the describing the Weibull function. If you want more information on that, let us know and we can get you more info. Given the time I've got, I'm going to skip ahead just a little bit. I'll show you the reliability life test. This is another sample size explorer where we're studying sample size, study length, or precision. So in this case, maybe we're interested in the plus or minus. How do we get that plus or minus number that's associated with each of these estimates down to a low level? So you'll find that under DOE, sample size explorers, reliability, and then this reliability life testing. Okay. When we're doing light bulbs, and like I said, the data were contrived that I showed you earlier, but sometimes if you're designing a light bulb, you want it to last a long time. If you're going to do a reliability test on that light bulb, how are you going to do that to accumulate enough hours or cycles on that light bulb before the market catches up with you and pushes you aside? You can't afford to do a test that long. Semiconductors, this is critical in semiconductor. How do you design a test when this semiconductor is supposed to last years and years and years before it fails? Well, you can't afford to test that long. So what do? Well, then we do something called accelerated life testing. And I've got a special data file here. This happens to be one that you can find in your sample data files called DeVault. And it's motors, I believe. This data set's a little bit different, set up just a little bit different than what I showed you last time. We've got the number of hours that have been run on these, we'll say, motors. So here in row 1, we put 5,000 hours on a motor, and it was still running. But it wasn't just one motor, it was actually 30 motors. So instead of, this is just kind of shorthand in JMP, instead of having 30 rows here that all say 5,000 censored, 5,000 censored, 5,000 censored, we can kind of condense things and say, well, this actually is times 30. And then row 2, this motor made it to 1,298 hours and it failed, and 1,390 hours and this motor failed. Now, also, we've got a column over here that says temperature. So these first 30 motors were all run at 10 degrees C. These motors from rows 2 down to 12 were all run at 40 C. Why did we do that? Well, these motors are sensitive to temperature. This particular failure mode is sensitive to temperature. So if we elevate the temperature, we should be able to accelerate or make these motors fail faster than if we ran them all at room temperature, something like that. So we've run some set of samples here at 40 degrees C. We've done some more at 60 degrees C and some more at 80 degrees C. And in each case, we've got some motors, in this last case here, just one, that made it out to 5,000 hours, which is the limit of our test. We aren't going to test any further than that. That's all we can afford to test. And we've got a number here that have failed in that time. So how do we handle this? We're going to go to Analyze and Reliability. And the second item down is Fit Life by X. This is our accelerated life platform. Our time to event is the number of hours that the motor lasted. The status is the censoring column. Weight is that multiplier kind of thing, so I'm going to put that in here as frequency. And then temperature is our accelerator factor. So I'm going to put that in here as my X. Now there are some relationships here. Arrhenius Celsius. So there's 3 different Arrhenius equations that kind of link these temperatures to each other in the reliability domain. We're working with Celsius temperature, so I'm going to keep it with that. If you had Fahrenheit or Kelvin, you could do that. If you're not working with temperature, sometimes you're working with increased stress or something like that. We've got a lot of other options down in here that can be selected depending on what model fits your data the best. And that requires some subject matter expertise to figure that out. So I'll just have to leave that at that for today. So we're going to stay with Arrhenius and Celsius, and I'm going to just say OK. Here again is our raw data. First thing JMP always gives you is raw data. Temperature along the x-axis versus the hours to failure with the log axis going up the y-axis. So we see here at 10 degrees, we didn't have any failures, marked with the little open triangle. At 40 degrees, we had several failures, but some made it up here to 5,000 hours. At 60 degrees, they failed even earlier, but some made it to 5K. And at 80, even earlier. This chart lets us see the relationship between, this would be the 10-degree failure line, the best fit 40-degree failure line for hours versus probability of failure, the 60-degree and the 80-degree failure rate. And we can choose different scales to see which of these models might be the best. We chose log normal earlier. We could choose Weibull if we wanted. And then finally, down here, we have those 3 models that we just did, Weibull exponential and log normal. It's given us distribution profilers for each. So we can compare one to the other How do we use this? Well, let's say the operating temperature that is the design for this particular motor is 30 degrees. So we'll say 30 degrees. And we want to know at 3,000 hours, how many of these motors would fail at 30 degrees. So now we can read across, and if we're assuming a log normal distribution, we would expect 0.4%. I think I'm reading that right. 0.4% if we assume log normal distribution. 2% if we assume exponential, and 1.5% if we assume Weibull. So you could try to determine which of these fits your model the best in order to select which one of these is appropriate for you. Or you could take the conservative route and say, I'm just going to assume that the exponential fit gives me the most conservative value, and so I could expect as many as 5% might fail, 0.046 on the upper end. at 30 degrees and at 3,000 hours.